There we go. If you have a di or a triprotic acid, it is only the first dissociation that is important. Okay, so only the first dissociation in polyprotic acids is important in Ka calculations. Diprotic acids do undergo 2 dissociations. Okay, but only the first of these dissociations produces significant quantities of H+. The second dissociation also produces some H+, but the Ka of the second acid is always so much smaller than the Ka of the first dissociation. Sorry, the Ka of the second dissociation is so much smaller, so the amount it produces is insignificant in comparison. Yes? Okay, so let us take a look at this question. What is the concentration of H+ in a 0.2 molar solution of carbonic acid? You should get a piece of paper, okay, because we're not going to, I mean, everything's written there for you, but we're going to do it off page. Because you learn more when you do it off page. You guys know that, right? Your brain uses more neurons and remembers things better and processes better when you write. Okay, so what is the concentration of H+ in 0.2 molar carbonic acid? So anytime you're asked for hydrogen or pH or anything like that, there are 2 questions you should ask yourself first. 1, what is the first question? Is it an acid or a base? And this one is really easy because it says literally acid. Question number 2, is it strong or is it weak? It is weak. Okay, if it was strong, St, you would use stoichiometry. But it is not, it is weak. So when it is weak, what do we use? Rice table and Ka. And you have to be careful here because later on, if it's an acid, you need to use Ka. If it were a base, you would use, guess what? Kb, okay? Did I tell this class last time? I usually, when we get to Unit 5 and we do stuff with bases, there will literally be a question that says, you have this weak base and it does blah, 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 blah. And people will then use the Ka. I'm like, what on earth are you doing? And it makes me want to bash my head against a wall. So please, please, please pay attention to that. Although this unit, there will be no bases because, well, other than strong bases, there will be strong bases, but not weak bases. Okay, so go ahead, try it. And remember, the concentration of the acid given in the question is always the initial concentration. Now, bearing in mind what I just told you, what should your products be here for the reaction? H3O plus, and HCO3 minus. And we're going to leave that second hydrogen alone, okay? This one here. Does not dissociate to a significant extent. Does not come off. I'm really glad to hear papers turning. That's a good thing. Where did I get this Ka value from? That comes from the data booklet. So if they give you a Ka in the question, use that. If they don't, you're going to look at the data booklet. You can write the minus x down at the bottom, okay, because we're plugging this one here. Is there another option to where you can write that assumption statement? You could, if you wanted to, do it up here, and then you would just leave the x out in your Ka, okay? So either way is good. If you left it out, in the Ka, it would just look like this, 4.3 times 10 to the minus 7 is equal to x squared over 0.20. So that would also be fine if you did it up above. Is there another way to say, assume x is insignificant? Yeah, assume X is forward-facing alligator, 0.20. Excellent. Okay. Yes. Oh, but the book forgot to square root it. Well, bad book. Fix. So then the concentration of H plus would be, how many sig figs should we have? 2.9 times 10 to the negative 4. And then you would want, of course, because it is a concentration, molar. Is good? Okay, excellent. Now, what if we were to have done the second dissociation? All right, we're not gonna actually do it. We're just gonna walk through it here. So this would be, let's see, it would actually be 2.9 times 10 to the minus 4. 2.9 times 10 to the minus 4 times 2.9 times 10 to the minus 4. We'll fix this as we go. 2.9 times 10 to the minus 4. 2.9 times 10 to the minus 4. What? Why is that even there? That shouldn't even be there. No. No. That should just be 0. This is dreadful. Oh my gosh. Okay, get rid of that. That should be, oh no, it is because we already have some. Yes, we already have some hydrogen. 2.9 times 10 to the minus 4. It is, because that's from the first dissociation. So now we have a new X. Yes? All right. So now what we have is we have the Ka for this one. We've got our products. We've got H plus and CO3 2 minus over HCO3 minus. So now we need the Ka for HCO3 minus, not for H2CO3, and that is 5.6 times 10 to the negative 11. All of these numbers in here would be 2.9 times 10 to the minus 4. 2.9 times 10 to the minus 4. 2.9. Oh my gosh, what a pain. 10 to the minus 4. 2.9 times 10 to the minus 4. 2.9 times 10 to the minus 4. 2.9 times 10 to the minus 4. Okay. 2.9 times 10 to the minus 4. And that would be, Okay. Okay. It's actually 2.9325. Okay. Times 5.6 times 10 to the minus 11. And that gives us, whoops, no, I shouldn't cross that one out. That's not the one I want to cross out. This is the one I want to cross out. This is 1.64 times 10 to the minus 11. Okay, so this should be 1.64 times 10 to the minus 11. And then I need to take my 2.9325 times 10 to the negative 4 plus 5.6 times 10 to the negative 11 equals 2.933, 2.9325. 2.9325 x. Anyone have a quadratic formula calculator they can toss? A equals 1, B equals 2.9325 times 10 to the minus 4, and C equals negative 1.64 times 10 to the negative 11. Anyone have that? Or you can just believe me. You can be like, okay, the concentration from the second dissociation is insignificant. It's tiny. I don't know what it actually is. Okay. Anywho, there we go. All right, so those are the dissociation of diprotic and triprotic acids. So just ignore the second dissociation. And now we're going to move on to page 98. Now we're going to go backwards. Yes? We're going to go backwards. If we are given H plus concentration, and if we are given the concentration of the acid solution, we can easily calculate the Ka value for the acid. So this is like the question where I give you an initial quantity and an equilibrium quantity and ask you to find KEQ. Yes? But here we're just calling it Ka. So we have an unknown weak diprotic acid, so you cannot find it on your table of acids. You might be given an acid that is not on the table of acids that has a name, and you'll be looking for it, and you'll be like, where is its Ka value? I cannot find it on here, and it's not there because you are to find its Ka using calculations. Does that make sense? Okay. An unknown weak diprotic acid is found to have an H plus concentration of 0.60 molar when we mix a 2.50 molar solution of the acid. Calculate Ka for this acid. Remember, only the first dissociation is important in a polyprotic acid. And also remember, is this concentration of the acid, is that the initial concentration or the equilibrium concentration? Initial. It's always the initial. Now, you might be given hydrogen, which in this case you are, which makes your life fairly straightforward, or you might be given pH, and then you would have to go from pH to hydrogen. Yes? Do you guys remember how to go from pH to hydrogen? Yeah, from pH to hydrogen. If you know the pH, how would you find hydrogen? Yeah. Okay. Concentration of hydrogen is equal to 10 to the negative pH. Okay. Whenever we give you the hydrogen ion concentration, is that the initial concentration or the equilibrium concentration? Always equilibrium, because what is the initial concentration? Always 0. Okay, so that's the equilibrium concentration of hydrogen. So when we first place H2 into the solution, none of the acid is dissociated, so the concentration of H2A undissociated is 2.50 molar. And is that what I actually wrote there? It is. That's convenient. And hydrogen and HA equals 0. So we've got 2.50, we've got 0, we've got 0. Now, is our change an unknown value, or do we have something down in the equilibrium section? We do have something down in the equilibrium section. We were told that the concentration of hydrogen is 0.6 molar. So we know that, and that is always an equilibrium concentration. From there, please don't write X, because it's not an unknown. X is used when it is an unknown. Oh, look, I've written it over here. Since you know the value of the change in concentration, use the number in the race table, not X. X is an unknown. All right, everything's 1 to 1 to 1 though, so our changes will all be 0.60. This one goes down, these two go up. And you'll notice that this number is actually, it makes a difference, doesn't it? Like you start with 2.50 and you end with 2.44. The problem is that sometimes people will put X in here, right? And then they'll fill in the numbers later. And then they'll do something like they'll assume X is insignificant, right? Because they're like, oh, I must assume that X is insignificant. But it's not an X. It's not an unknown. And it is certainly not insignificant. And you save yourself that grief if you don't use X unless it is truly an unknown. Okay, so we've now got our values. We've got 2.44, we've got 0.6 and 0.6, so that's 0.6 squared. We've written our Ka expression, including Ka equals, and we get 1.475 times 10 to the minus 3, and that would round to 2 sig figs, because these numbers here have 2 sig figs. So 1.5 times 10 to the minus 3 is good. Okay. Common error. Look how much I care about this. Since students will write X in the ICE table and then assume X is insignificant. If you were to do that, you would get 1.4 times 10 to the minus 3, which is not the same as 1.5 times 10 to the minus 3. Yes? Okay. Ooh, here we go. So you guys are going to get your piece of paper and you are going to cover up the answer, all right, and try this one on your own. And if you're like, well, what do I call this acid? You can either call an acid HX, because there is no element X, or you can call it HA. Those are very commonly used unknown acid formulas, okay? Where do we go from here? We need to find the equilibrium concentration of hydrogen. Are we given that in the question? No. Can we find it from information in the question? Yes. Go for it. Thank you. No problem. Thank you. Yeah, right there's great. Thank you. Have I calculated my hydrogen ion concentration correctly? Yes? Good. Okay. Now, one thing you're going to notice is that when we do our subtraction here, we get the number 0.024999444. Yes? Is that to significant digits any different than 0.025? No. So in this case, you can just round this to 0.025. Yeah? And it turns out that this value was insignificant. but it won't always be insignificant. Sometimes it will, sometimes it won't. It's a known value, so you might as well throw it into your calculator and see what you get. Yes? Or at least you can look at the value and be like, 10 to the minus 7, that's so much smaller than 10 to the minus 3, which is my last digit in the 0.025. Yeah? And because you guys are in AP, I am going to encourage you, rather than simply writing the dissociation, to use the water and the H3O plus, because those are that's the formula that they give you for Ka and all of that in the AP data sheet, on the AP data sheet, okay? Woo, that's a fun number. 1.23456, and then there's a 9 times 10 to the negative 11. But we're going to round that anyway, so. Did I get it right? Yeah? Cool. Okay, so really, other than the fact that we're now tacking on some pH calculations and things like that, this is exactly like your equilibrium unit, right? You were asked to find KEQ, or you were asked to find an equilibrium concentration, yes? So very, very similar. There is one more type. We're going to finish this unit tomorrow. You have a quiz tomorrow. Now, I'm actually, yeah, we have a quiz tomorrow. It's really stupid because I looked at the calendar and it would make perfect sense to have your KA quiz on Monday the 3rd and then test you on Friday the 7th. Yes? But Friday the 7th, there's the Remembrance Day assembly. So we cannot do that. So I'm going to test you on the 10th of November, which means we're going to be like a week gone on finishing this unit. Okay? And there we are. What can we do? It's either that, there is another choice, choice number 2. I give you the pH quiz as a practice quiz to take home, and I give you your Ka quiz on Friday, and oh crap, there's lockdown drills. Oh no, that's next week. That's next week. We're okay. Okay. I could give you your Ka quiz on Friday, get it back to you on Monday, and we can test on November the 5th. So you get a practice take-home quiz on pH. And then you could have your Ka quiz on Friday. Okay. So let me write down your 2 options here. We have, this pen is not working. That's great. Option A. pH quiz tomorrow. Well, there's actually a third option as well. PH quiz tomorrow. KA quiz Monday the 3rd. That's next Monday. And then your test on Monday, November 10th. Okay, so that's option A. Option B is to have your PH quiz tomorrow. No, there's an option C. Tomorrow, KA quiz Friday. And your test on Wednesday, November 5th. Option C, take home practice PH quiz, which I could give you today if you want, if you're ready for it. Or I could give it to you tomorrow, it doesn't matter. KA quiz Friday. Test Wednesday, November the 5th. Are there any options we would like to get rid of right off the bat? B, that's what I thought. I thought no one would like that. That's okay, because I don't want to mark that many quizzes anyway. Okay. Not in that short of a time span. Not while I have report cards I need to do. Huh? Oh, so you don't want to write a test for one of the 3 easiest units of the year? We'll just have the two easiest one and then the 3 harder ones? Does that sound better? Okay. Okay. Anyone need any more time to think about it? Yes, you have a... No. Otherwise, we're dragging this out, and it means that we will not finish electrochemistry. Yes? And if we don't finish electrochemistry, that means you walk into the AP exam going, well, this is interesting. Yes? Anyone have any more discussion points they'd like to put forward? Anything you would like other students to consider? You'd be like, yes. I agree with you on that. I feel like this would lead to procrastination. Are you going to spend all that time studying for that test? No, you're not. Yes.
Well, like, if it's on a Wednesday, it's the day before, it's like Wednesday.
And the day before it's my birthday.
You have all okay. We're finished by Friday, right? We're finished by Friday. You study all of Saturday and Sunday. Yes? You pretend your test is on Monday. The only reason it's not on Monday is because I need to give you your quiz back so you can look at it. The only reason it's not on Tuesday is because Tuesday's classes are shorter. Do you know what I mean? The reason it's on Wednesday rather than one of the 2 days before it is because the other 2 days are not nice test days. So study here. You can ask questions on Monday, right? You can ask questions even on Tuesday if you need to. And then, bam, your test is on Wednesday. Doesn't that sound like a good plan? Yes. I think so. And Juno thinks so. And she was very direct and open about that. And I think we're going with option C. Would anyone like the practice quiz today? Okay. Treat it like a real quiz. Okay. Give yourself... 1, 2, 3. Anyone else practice quiz? Yes. Anyone else want to practice quiz today? If I don't give it to you today, I'll give it to you tomorrow. Okay. And I have things here for Sarah. And Anna. And Taran, you open anyone over here. No. There you go. Taran, you. Does anyone want a paper clip? Give me paper clips and I hate them. No? Okay. Ugh. Okay. So let us then finish off KA calculations. Okay? We have one last type, and that is calculating an initial HA. So a question like this might read something like, what was the concentration of the acid? And what do you know about concentration of the acid? Concentration of the acid is always initial. So nobody's going to be like, what is the equilibrium concentration of the acid? It's so not a thing that we will, like, it doesn't even get referred to that way. Yes? It's always the initial concentration. So if you're asked for the concentration of the acid, it is never the equilibrium concentration. Now, in this particular question, we've made that very, very obvious by saying how many moles of H2CO3 were initially added to the sample. Okay, so we've got that initial thing in there, but that might not be there. Okay. So let's take a look at this. We have 500 milliliters. Okay, that's good. Of our oxalic acid, H2C2O4. And we have a pH of 1.095. How many moles of H2C2O4 were initially added to the sample? So we're dealing with an acid. And is this acid strong or weak? It is weak. And if it is a strong acid, or sorry, if it is a weak and it is an acid, what are we going to be using? Rice and Ka. And quite frankly, even if you don't know what to do with a question like this, you can be like, I have a weak acid. I should draw a rice table. Hence, you get at least 0.5 marks, right? You might not fill it in correctly, but you're getting 0.5 marks because you've written a reaction. Yes? If you're like, oh, I've got a pH. Oh, dang. What do I do with that? Even if you're just like, oh, probably if I've got a rice table, I need a concentration. Turn that into hydrogen, yeah? And even if you don't know what to do with that later, you've gotten yourself another half a mark. Yes, and if this question is out of 4, you now have 25% rather than 0%. And plus, having those values might help you be like, oh, I know where these things go. Huh? No. What you would need to do is you would need to show this. I would show H plus is equal to 10 to the negative pH. I would actually write this. And the reason is that it just makes it easier for somebody to follow. Yes? Is good? So now you're like, I have a half a mark. Okay, because I can do that. And I know that I'm doing rice and Ka, so I'm going to write my ionization of H2CO4, H2C2O4, sorry. This one I'm going to write as like the shortcut method just to show you, okay? Is it going to be like this? Is that correct? No. Remember, it is only the first dissociation that matters. So that's going to be HC2O4 minus. What do we actually know in this table?
Concentration of hydrogen.
We know the concentration of hydrogen. Okay, so that is, and is that initial or equilibrium? Equilibrium. Do we know anything else?
So the concentration of H.
Yes, because this went up by 0.08035 and it started at 0, because they always start at 0. The right-hand side always starts at 0. And the 2 ion concentration should be the same. And you may think, wow, why is she keeping so many digits? Well, I actually have more than that in my calculator. I have 0.080352612, and I just haven't pressed clear. Okay? All right. Anything else I need? Well, I need my H2C2O4. Can I fill in anything in that H2C2O4 column? I can fill in the change. It's going to go down by?
0.08035.
Yes. Okay. What's my initial concentration?
Yes.
That's what I don't know. You can call this X, or sometimes if you want to, you can call it CI, which stands for the initial concentration. If you're like, oh, I like having X for my change, right? If you find that confusing, you can use instead of X, but X is fine. Okay, so now we have X minus 0.08035. And now, even if you filled in nothing in that table, even if you were like, I don't know what goes in that table, you know that you should also write a K A expression. Yes? So for a half a mark, you're going to write a KA equals H plus times H C2O4 minus over H2 C2O4. And then, of course, we can plug in our equilibrium concentrations, 0.08035, and that's going to be squared because I got two of those on the top. And I got x minus 0.08035. And you know what? I put that whole number into my memory. I did shift memory in. Let's see if it'll recall it for me. Memory recall. It does. Okay, so if you got a memory button on your calculator, you can get that whole number to stick into the memory. Well, I can't solve this. What do I need to solve it? I need a KA. So where is my KA? I've got data booklet H2. 5 point what? 5.9 times 10 to the negative 2. Thank you so much. 5.9 times 10 to the negative 2. Now, I'm going to tell you something that I am embarrassed to admit. I used to solve this way. Don't write this down. And I used to be like, oh, okay, 5.9 times 10 to the negative 2x minus. And you're like, hang on, isn't this how you solve it? No, the x is not insignificant. But does anyone see where I'm going? Is there a more efficient way to do this? You can just switch this and this, and you save yourself all of this nonsense here. Yes? So it took me years, and I had to see a student doing it, and I watched them do it, and I was like, oh, why did I never think of doing that? I was so mad at myself. I mean, I've known about it for like years and years and years now, but still, I don't know how many years I was teaching before somebody had and I was like, probably 4 or 5 years. Anyway. Okay, so we have now x minus 0.08035 is equal to 0.080. You'll still get the right answer doing it the other way, but it's just less efficient, over 5.9 times 10 to the negative 2. Okay, so we now got squared divided by 5.9 times 10 to the negative 2 equals and I think we have 3 sig figs. I think.
That is 2.
Let's see. We've got, oh yeah, 2 sig figs because of the Ka value. Yeah, you're absolutely right. So 2 sig figs, so that will become 0.19 molar equals the concentration of H2C2O4. 2 sig figs because of the Ka value. Yeah? Oh yeah! Aren't we looking for the moles? Ay. Always go back and look for what the question was asking. Okay, so this would be that molar, that, well, I suppose I don't need to cross that out. I will just, well, maybe I will. Here we go. Concentration of H2C2O4. That's that molar. And so the moles of H2C2O4 is equal to, well, we know that we have 500 milliliters, or 0.500 liters, yes? And we know that molarity is really moles over liters. So we can then calculate it 0.500 liters times 0.18979 moles per liter. The liters will cancel out. And we get 0.0949, which will then round to 0.095 moles of H2C2O4. Is good? Okay. So you have now learned all 3 types of Ka problems. Yes? Yes? Yes. Yeah.
You got to 0.0835 from plugging the pH into the concentration of the hydrogen, right?
Yes.
So it was like H plus is equal to 10 to the power of negative 1.095.
Yeah.
Oh, okay.
Right there. Yeah. You good? Okay. And what else you missed is you missed finding the Ka given a hydrogen ion concentration or hydroxide ion concentration and an initial acid quantity. But this is just like KEQ, right? Like I give you an equilibrium value for one of them, I give you an initial value for one of them, and then
the one you just showed, you need to use like logs. Okay.
Yeah. So I could give you the concentration of hydrogen here, or I could give you a concentration of hydroxide and you would need to use KW to find hydrogen. I could give you a pH and you'd need to use that, to find the hydrogen. Okay? Yeah. So when is class over today? 16, 19, so we have 10 minutes. I don't want to teach you anything else today. Do you feel like you would like to do example 2 of this kind?
Is it the same?
It's the same basic thing. Do you want to give it a go? Yeah. Give it a go. See how it goes. This is on page 101. The other thing, Tony, is I gave people the practice quiz for the pH because we're not going to do it in class tomorrow. Okay.
So wait, the hydrogen is on Friday, it's just on Friday.
Yeah, just Ka quiz on Friday. Okay.
Wait, is it always? You don't just write it like instead of just write it. Just say this turns into H plus. You can write like this. So I can
This is too small. Yes, we get some extra.
It doesn't matter. What was for this one? I thought.
You always know. You know I'm always going to have to say. My mom has my watch.
No, but she's like, yeah, that's fun.
1 second, I got Cynthia and then you.
Same question.
Okay. Yes. I would use ionization all the time for acids. All the time. All the time. Even though strong weak, I would use ionization all the time because you guys are wasting. Because in reality, ionization is what happens. Yeah, does that make sense? I would use dissociation if I was doing a strong base, and that'll pick up. That's so like LiOH, because there's no way to go.
But do you always have right?
I would, because you're in AP, because the AP data book gives everything in terms of H3. Okay?
Wait.
Yeah.
Isn't this is an acid, right?
That is an acid.
But then
So if you end up with OH, you've done something wrong.
wait, my students. Oh wait, I'm not screwing up.
I would, if you're taking AP, yeah.
Wait, Miss Spence.
And that's because the H3O plus.
Oh, Ryan, you feel your race. I never always mind.
Apparently.
Wait, which H do you take away? Is it HCOO or a COO? What? The back one is the roll. Y'all got it.
This guy said water's plus.
Is the water more safe? Not. Wait, what's the status of these two?
Unless you're, yeah. It doesn't.
Yeah, I think in this case, water is less likely. No, it's because the other one's not.
What time is it? Brian, what time is it? I need time.
6 or 7.
Is John just not? Yo, John, what's good, bro? Is he still recording? Hey, John.
This guy said water's more.
Oh, real.
Said water's
Yes.
Is ionization just for acids or is it for bases?
Bases as well, but not Bronsted or not Arrhenius bases,
Oh.
like metal hydroxides. I would always do ionization unless I have a metal hydroxide.
Oh, because like, I mean, the 4.1 part, where it said like dissociation, I think it mentioned a lot for bases. So
Yeah, and that's because in Chem 12, like regular Chem 12, I'll tend to accept either one. But I would say because you guys are taking AP and because the AP booklet gives you, right, like if we look at all our formulas, where is it? Right, it gives you H3O plus, H3O plus, H3O plus. So I would tend to go that route. Yeah.
you.
Yeah, no problem.
Oh, Oh, this right? Oh, it's like this as zero. And this would also be zero. 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 This. One. What? You're taking the cheat. What do you mean this? No, no, the initial office part. Yo, what? No, what the hell? No, I'm not autistic.
And one thing you should notice about this question is it just says find the concentration of the acid. It does not say initial concentration. So you need to know that whenever you want finding the concentration of the acid, that is always the initial. Okay? So there's a reason I keep harping on that. Yeah.
Wait, I'm stupid.
I'm confused with like,
Oh my.
Oh, yeah.
what if I have like a 7.5 here? So the 7.5 here will go. This is a pH, right? So
Mhm.
7.5 we have.
Wait, the
like,
water just gets
this
ignored, right?
as
Okay, I'm
7.5.
not, like, I don't have the question, Brian, you can have fun.
Well, why would your calculator ever give you?
I don't know.
No, it won't.
Yo.
So only like
Yeah, it'll only give you whole numbers. Yeah,
much easier.
right?
Also, the one was a K W. So whenever we have water,
Mm-hmm.
we can use K W.
Yes.
As long as we have water, we can.
Yes, absolutely.
So-
And anytime you have an acid or a base, you'll always have water because they can't be acids and bases unless they're in
Right, so
solution.
KW is always.
Always
can be
a candidate, yeah.
Thank you.
Yep, yep, you're welcome. Oh, thank you.
Oh, why won't the water?
So I would say for homework tonight, a good use of your time would, if you have the time to do it tonight, would be the pH quiz. If you do not have the time, then I would say page 99, 102, 103. Yeah. I'll make sure it's up on Teams. Okay? Anybody else need the pH quiz? We're good? Okay.